And I'm going to share my screen. Let's see if I need the calculator quite yet. Not yet, so we can just do, there we go. So 8.5 is talking about probability distributions and specifically expected values. And so we're going to talk a little bit about what these mean before we get into actually calculating expected value. So we have this idea of a random variable. And a random variable is a rule that assigns a number to each outcome of a chance experiment. So let's say we consider tossing a coin 3 times and observing the number of heads. Let the random variable x denote the number of heads that occur in 3 tosses. So let's think about our tosses. And give this a number 1 so we can organize our work. So if we think about the 3 tosses, what can we have? Well, we can have 3 heads. We can have 2 heads and a tail. We can have a heads, a tail, and a heads. We can have heads and then 2 tails. Then we can start with a tail and have 2 heads. Again, this is all going back to our, our tree diagram of when tossing the 3 coins or tossing the coin 3 times. So the next we can have a tail and then a head and a tail, a tail, a tail, and a head. And then our last one could be 3 tails. So we think about this as a sample space. Kind of going back to what we did in our last chapter. Remember, in order to define a sample space, we have to say S equals, and then we have it in the curly brackets because it establishes that as a set. So if we think about, we're declaring X be the number of heads that occur in 3 tosses. So we create a table. Let's look at our outcomes. Well, and the value of X. So the outcome heads, 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 we are going to have X equals 3 because there are 3 heads. Again, X equals the number of heads in the toss. Okay, for the outcomes heads, heads, tail, there's 2 heads. For the outcome heads, tail, heads, again, there are 2 heads. And for the outcome tail, heads, heads, again, there are 2 heads. We switch now, and we're going to go to tail. Oops, tail. Let's see which of them. Hold on. So if we think about our 2, first of all, let's just circle those in our. So heads, heads, tail, heads, tail, heads, tail, heads, heads, right? Those are where we have our 2 heads. We've already used the 3 heads. So now what do we have left? We have when we have a single head, right? So where are those? Well, the single heads, we've got heads, tail, tails. That's giving us 1. We've got tail, head, tail. That's another 1. And we've got tail, tail, head. That's 1. And then the last outcome we have is tail, 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 which is 0 heads. So what this means is that there's either 0, 1, 2, or 3 heads. So the set is what we call the range of X. So let's look at number 2. Number 2 says, suppose we would like to find the event that exactly 2 heads comes up. What does this look like? So if we want x equal to 2, well, where in our table do we see x equal to 2? Well, we see x equal to 2 right here. So what that means is that we have the set head, head, tail, head, tail, head, and tail, head, head. So and if we wanted to find the probability that x equals 2, there are 3 outcomes where that happens out of the total 8. Also, we can think of other events to consider. Let's say we have the event where x is greater than or equal to 0, but less than or equal to 1. What this means is that we have 1 or no heads, and therefore the probability that x 0 less than or equal to x, which is less than or equal to 1, is going to be 1/2. Why is it 1/2? Well, 0 or 1 heads is this whole section of our table. We can see there's 4 outcomes, 4 out of the 8 outcomes, which is 1/2. So what we're doing here is we're defining our variable x to represent something, and then we can use that to find probabilities because we are setting up parameters for it. So I want you to look at this example. So suppose we have an experiment where a coin is tossed 3 times, and we have the following sample space. Let y be the random variable that is the number of tails observed. Which of the following events is the event that y equals 1? So we're looking at which of those is where we have 1 tail. So go ahead and send me your message in a direct, or send me your answer in a direct message. So if we look at this list, A, B, C, D, E, which of those letters has only 1 tail occurring in each of the outcomes? That's what I'm asking. Okay, so if we just want y equal to 1, and remember, what is y? We have declared that y is the number of tails observed. So y equaling 1 means we want tails to equal 1. So in outcome A, we have situations where we have 2 tails happening and 3 tails happening. So that's not going to work for us. B is the null set, which means that it doesn't happen at all, which is not true. We can get a tail. C, we've got 2 tails. So this would only be true if we were saying, what about if y equals 2? D, we have 2 tails and 3 tails. So this is y is greater than or equal to 2. And then E is 1 tail. So this is our answer. This is where y is equal to 1, which again means that we want one tail to occur. So again, what we're doing is we are just representing our outcomes using a variable instead, okay? So recall that we define the probability distribution for an experiment. Each outcome is assigned a probability between 0 and 1 inclusive, and the sum of the probabilities of the outcomes had to be 1. We now define the probability distribution of a random variable similarly. So if the random variable x assumes values x1, x2 up to xn, then the probability distribution of the random variable is the assignment of the probability to each value that can be expressed in the table. The two things that they're talking about here, it must satisfy the two conditions, is that the probability of the outcome must be greater than or equal to 0, but less than or equal to 1, and that the sum of the probabilities, so this is representing the sum of the probabilities, needs to equal 1. So at first, this feels very weird, okay? All I'm trying to say is that, we're looking at these outcomes, and instead of thinking about them individually, we're assigning something to them. So let's look at an example where it makes more sense. So if we're returning to the example where we flip a coin 3 times, and the random variable x is the number of heads observed. So each of the events, x equals xi, where xi is 0, 1, 2, or 3, has a probability associated with it, which we can find just by counting the outcomes in the sample space. So first of all, there's 8 outcomes in the sample space. We think about xi being 0. This means no heads. Well, that only occurs one time right here, the tail, tail, tail. So that's 1 out of the 8 times. So there's a probability of 1/8 that we would get no heads. For the next outcome, xi equaling 1, that is 1 head. And that comes from the events that we have head, tail, 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 head, tail, and tail, tail, head. So there's 3 outcomes here out of the total 8 outcomes, which we can see then that the probability is 3/8. Xi equaling to 2. That's 2 heads. And if we think about that, that's going to be head, head, tail, head, tail, head, and tail, head, head. There are 3 of those again out of the total 8. So again, that's why we end up with a probability of 3/8 of getting it. And then lastly, xi equal to 3 means we want 3 heads. And there's 1 time that occurs out of all 8, so that's why it has a probability of 1/8. If A is the event that the 3 heads are observed, we write the probability of A equals 1/8. If X is the random variable that is the number of heads observed, we write the probability of X equaling to 3, which equals 1/8. If X is a random variable, the expression P of X is meaningless. The input into the probability function must be an event. So all I'm trying to say here is that X must equal something. So this is, again, just a new way of thinking about how we're organizing our work. Let's go to the next page and see how this relates to other areas of probability. So the probability distribution can be graphically exhibited using a histogram. So to draw a histogram of the probability distribution, we denote the values of the random variable along the x-axis. So you can see 0, 1, 2, 3 along the x-axis. And then above each value, we draw a rectangle of width 1 and height equal to the probability associated with that. Since we can make the rectangle of width 1, the area of the rectangle associated with any value is numerically equal to the probability associated with that value. So again, we can just see we've got the 1/8, the 3/8, the 3/8, and then the 1/8, and it's a histogram, excuse me, because they touch. Okay, we don't want to have a bar graph. And again, the thing you want to know in order for it to be a valid distribution, the sum of the probabilities must equal 1. Another thing we can think about, so suppose you want to compute probability that x is greater than or equal to 1, but less than or equal to 2. So we want to represent it graphically in the histogram. So when we think about the histogram, where is that happening? Well, it's happening right here. This is the places where that's happening. So the probability of x less than or equal to 1, but, or excuse me, greater than or equal to 1, but less than or equal to 2, is the probability that x equals 1 plus the probability of x equals 2. So from our histogram, we can pull that information because we see the box where x is equal to 1 has 3/8 for its what it represents, the area there. Probability that x equals 2 also has 3/8. So we can add those together, giving ourselves 6/8, which we know we would then reduce. So again, when we add up all the bars in a histogram, because those bars represents the probability, the individual probabilities, they need to equal 1. So if we look at our next page, we have a histogram, and I want you to tell me if it depicts a valid distribution for a random variable, why or why not. So think about what I was saying. In order for it to be valid, the sum of all the probabilities there has to equal 1. So if we're checking if this is a valid distribution, let's look at what each of the bars represents. Well, the first bar represents the probability of 1/8. The second bar represents the probability of 4/8. Then we have 3/8 and 3/8. So if we add these probabilities up, one plus 4 is 5, plus 3 is 8, plus 3 again is 11, and we get 11/8, which is not equal to 8/8, which is what we would need it to be for it to equal 1. So this is not a valid distribution. Okay, let's look at our next. So suppose a pair of dice are rolled. Excuse me. Let x be the random variable that corresponds to the sum of the two numbers observed on the dice. So So before we even get into finding the probability distribution or drawing the histogram, let's first just remember our table that we used back in chapter 7. So if we have our first die and our second die, we have the numbers 1, 2, 3, 4, 5, and 6. And we're going to use this table to represent the sum. So if I roll 2 ones, I'm going to get a 2 for my sum. 1 plus 1 is 2. If I roll a 1 and then a 2, I get a 3. I roll a 1, then a 3, and I get a 4 as my sum. 1, 4, and so forth. So we can just fill in our table. And we can see what are our possible sums. So our possible sums go from 2 to 12, right? Because again, what we're doing is we're focusing on the numbers that are inside here, right? So if I have my 2 black lines, those are the outside, those are representing what the actual dice are, but inside there are the possible sums. So we're letting X be the random variable that corresponds to the sum. So if we create a table, we're going to call the first column XI. The reason why it's called XI is because there's different outcomes at each of these places. And so our first possible sum is a 2, then a 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the second column, we're going to say, what is the probability that X equals XI? And all that part is saying, again, this notation all that means is the probability that the sum equals a specific value. So what is the probability that the sum equals 2? Well, remember, there's 36 total possible outcomes here, assuming that order matters, right? We're assuming that we roll dice 1 and then we roll dice 2. So 2 occurs once out of our 36, so it has a probability of 1 out of 36. 3 occurs twice, so it has a probability of 2 out of 36. 4 occurs 3 times, so it has a 3 out of 36. 5 occurs 4 times, so we have 4 out of 36. 6 occurs 1, 2, 3, 4, 5 times, so 5 out of 36. 7, 6 out of 36. I didn't give myself very much room in between these numbers. And then what happens after 7? Well, our sums start to go down. So now 8 is going to be a 5 out of 36. 9 is 4 out of 36. 10 is 3 out of 36. 11 is 2 out of 36. And 12 is 1 out of 36. So we have created the probability distribution. Again, this part right here is the probability distribution. So we now want to transfer that to a histogram. So if we're going to draw a histogram, we're going to make the horizontal axis is going to be the values that are in XI, meaning those are our outcomes. So if we think about what is the first possible outcome we can have, we can have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So those are what go on the horizontal axis. The vertical axis is the probabilities. And so we want to go by increments. So the first increment we're going to have is 1/36, and then 2/36, and then 3/36, 4, and 5, and 6. And that's as high as we need to go because that is our maximum probability. Again, you want to make sure that on your y-axis, the vertical axis, you're going by consistent unit. We're increasing by 36s here. So now we're going to just transfer. 2 has a probability of 1/36. So we're going to draw our bar like that. 3, the outcome has a probability of 2/36. So we'll draw our bar. 4, and then 5, and 6, and 7, then 8 comes back down. It's not very good freehand. And again, just from the distribution, we can see what is the outcome that's most likely to happen. Well, that means the outcome that's most likely to happen is a 7. Okay. So how can we, well, we can see that the outcome is most likely to happen. What can we do to calculate that? And that's where we get into this idea of expected value. So let X denote a random variable that assumes values X1, X2, Xn with associated probabilities P1, P2 up to Pn respectively. The expected value of X is given by, and you'll notice what's happening here is it's the outcome times the probability. So you can see the expected value is the sum of the outcomes times their probabilities, their individual probabilities. So let's look at an example here. So in a package of 10 microwaves, there are 3 broken ones. The quality control engineer tests a random selection of 4 of these microwaves. Let X be the random variable that is the number of broken microwaves in the quality control engineer's sample. Find the expected number of broken microwaves in the sample. So first of all, something we need to know, these are not independent events. Which means we can't use binomial probabilities like we were using in 8.4. We have to go back to what we were doing in 8.3 and use our combinations. So because there are 3 broken microwaves, that means we can have 0 broken, 1 broken, 2 broken, and 3 broken. So the probability that we select 0 broken microwaves is the combination of 3 broken taken none times the combination of 7 good choosing all, I'm choosing here 4 of them. So again, how am I getting these numbers? Well, there's 10 total. 3 bad. So 10 total, which breaks into 7 good, 3 bad. We are selecting 4. So we're taking a sample of 4 of them, which means that we're always going to have the denominator is going to be the combination of 10 microwaves taken 4 at a time. So that's a probability of 0. Probability of 1 is going to be the combination of 3 items taken 1 at a time times the combination of 7 items. And we only want to choose 3 now. Again, we're choosing 3 because we want a total of 4 We want 1 bad, so we need 3 good. And again, this is going to be over the combination of 10, choose 4. We can have the probability of 2, which we're going to do combination of 3 items, choose 2 bad ones, times the combination of 7 items, choosing 2 good ones, out of the combination of 10, choose 4. Again, remember, we keep talking about this, but these 2 numbers have to add to be that bottom number, okay? And then finally, we have the probability of 3. And this is going to be the combination of 3, choose all 3, times the combination of 7, choose 1, the combination of 10, choose 4. So I want you to calculate these 4 probabilities. I want you to leave them as fractions, okay? So go ahead and calculate these 4 probabilities. Leave your answer as fractions, and send them to me when you're finished. So we're going to pause for a minute so you can calculate these. Again, leave your answer as a fraction. so the probability of 0 is 1/6. The probability of 1 is 1/2. The probability of 2 is 3/10. And the probability of 3 is 1/30. So if we write a probability distribution for the random variable x, that distribution is going to look like this. So we have x, which would be our outcome, and our possible outcome is 0, 1, 2, or 3 broken. The probability of that happening, which we denote as x equals xi, again, the probability of 0 is 1/6. The probability of 1 is 1/2. Probability of 2 is 3/10. And the probability of 3 is 1/30. So to find the expected value, which is the question they're actually asking, these problems, they take a lot. And the thing I like about this is it kind of brings everything together we've done in chapter 8 into one unit. So find the expected number of broken microwaves. So remember, expected value is the outcome times its probability. It's the sum of those. So we have 0 times 1/6 plus 1 times 1/2 plus 2 times 3/10 plus 3 times 1/30. So 1 times 1/2 is 1/2. 3/10 times 2 is going to be 6/10. And 3 times 1/30 is 3/30. If we reduce, we've got 1/2 plus, what is this? That's going to be 3/5 plus 1/10. 1/2 is 5/10. 6/5 we should have left is 3/5, excuse me, 6/10 and 1/10. And this gives us what is this, 12/10, which becomes 1.2. I know it feels weird to be like, well, how can you have 1.2 of a microwave? This is an average, okay? Expected value is an average. So on average, we can expect to get between 1 and 2 broken microwaves when we do this sampling. We can also use our calculator to do all this stuff for us. And so here's the steps we want to follow. So let me reshare my screen so that you can see the calculator come up. Okay, so to use the calculator, we want to enter our list into L1 and L2. So enter X in L1 and P of X equaling, so Xi in L2. Then we want to run one var stats. And then we do L1 comma L2. So what does that look like in our calculator? So if we turn it on, remember to get to the L1 and L2, we need to hit the stat key. Okay. So again, to get to L1 and L2, use the stat key. So under the stat key, we're going to press enter for edit. You want to probably clear these out. Remember to clear out, you're going to press up. When it's highlighted in L2, we press clear, and then we're going to press enter. Going over to L1, we'll press up, we'll press clear, and we'll press enter. So now in L1, we're going to enter our values for Xi. So we have 0, 1, 2, and 3. In L2, we can enter the probabilities associated. So for 0, we have 1/6. For 1, we have 1/2. For 2, we have 3/10. And for 3, we have 1/30. So once you're done entering those, you're going to press second quit to get out of that. We're going to press the stat key again. We'll go over to calc. And then the first thing comes up is 1 bar stat. So we're going to press enter. And then we need to put in the L1, L2 part. So to get that, remember, we're going to use the second key and then number 1, which is where L1 is, comma, press the second key and L2, because that's where L2 is, and then we press enter. And it gives us this big readout. What we're looking for is X bar. And X bar, that is just, it means the mean or the average. So we can see that we're going to use that X bar value. And as we can confirm, X bar is 1.2. And oh, look, we got 1.2 as well. It's a lot, I know. So any questions about, so first of all, how did I know that these were not independent events? So we think about what we did in 8.4. The probability was being, reported as a percentage, and this was not. This was being reported as a certain specific number out of a total, okay? And so that's what makes it not a binomial probability. It's not an independent event. It's dependent on this already given sample of 10, and we know in that sample 3 are broken. So knowing that it's not independent means that we have to use those combinations to calculate the probabilities versus using binomial probabilities like we did on Wednesday. And again, you want to find all the individual probabilities, then you can find the expected value. So the next one is very similar to the one we just did. So it says there are 11 monitors, 2 of which are defective. Find the probability distribution for the number of defective monitors, in a sample of 3. How many defective monitors do we expect to find? So we're sampling 3. We can have 0, 1, or 2 defective. So because it's only 0, 1, or 2, why is it 0, 1, or 2? Well, there's at most 2 defective, right? So we can't have 3 defective because there's only 2 total that we could even choose from. So knowing this, we're going to say let X equal the number of defective monitors. You have to define your random variable. Again, we're defining a random variable X to be the number of defective monitors. And so the other way we can do a probability distribution is horizontally. So if we have X sub I, we have 0, 1, or 2. And then the probability of that possibility, which is X equals X sub I, and we need to find those probabilities. So we're going to end class with you calculating those probabilities. So go ahead and send me your answers. And then we'll talk more about it on Monday. So we're just going to take a couple more minutes where you can look those over, calculate those individual probabilities, think about what we did in the last example. So again, if we're thinking about setting this up, we've got 11 total, 2 bad, 9 good, right? So then the probability of none, selecting no bad, is going to be the combination of 2, choose none, and the combination of 9, choose, when we're choosing 3, out of the combination of 11, choose 3. The probability of 1 is going to be the combination of 2 bad, choosing 1 of them, times the combination of 9, choosing 2 of them, because we still need 2 good ones to make up our whole sample of 3, out of the combination of 11 monitors, choosing 3. And then we've got the probability of 2 is the combination of 2 bad, choosing all 2 of them, times the combination of 9, still choosing 1 because we need a sample of 3, so we still need to add a good one in there, out of the combination of 11, choose 3. So that's where we're going to pick up when we meet each other on Monday. Go ahead and calculate those probabilities. If you want to do them as decimals, take it out 4 decimal places. If you want to write it as a fraction, that's fine too. Don't worry about reducing your fraction. And again, that's where we'll pick up on Monday. Okay. So don't forget, you've got, what is today? Today is the 12th. You have 8.4 homework due tonight. So don't forget to get that done. And then, like I said, we'll just pick up with 8.5 on Monday. Let me know if you have any questions. Shoot me an email, and I will see you all on Monday, okay? Bye, everyone.